Je voudrais remercier tous les membres du jury et puis Manuel d'avoir accepté de participer en visioconférence. Monsieur Manuel Sanchez, vous y disposerez de 45 minutes de présentation et ensuite il y aura un temps de questions-réponses de la part du jury. Hello everybody. I would like to thank you all the members of the jury for agreeing to participate by video conferencing. Manuel Sanchez, you have 45 minutes for your presentation. It will be followed by a moment for questions from the jury. And you can start when you are okay.
Okay. Thank you, Professor Aldin. Okay. Can I start?
Yeah.
Yes.
Okay. Good afternoon, everyone. Thank you for attending this presentation on which I will be talking about my doctoral thesis entitled Autonomic Processes for Integration in Industry 4.0 that was developed in co-tutela between the University of the Andes in Venezuela and the University of Pau in France. My supervisors are the Professor Ernesto Expósito and Professor Jose Aguilar. The presentation was divided into several sections through which I'll describe the topic under study. First, I'll present the context, which is related to the Industry 4.0. Next, I will describe the problematic, starting from the challenges, state of art, and my thesis objective. Then I will place my contributions, which are first, an autonomous integration framework for Industry 4.0. Second, a communication module, multi-agent system, and cloud computing services. And third, shared coordination, autonomy cycle, and the implementation of a shared supervisory system. Then I'll finish with some conclusion, perspective, and publications. I'm going to make a short introduction to the Industry 4.0 context and its evolution. Since its inception, industry has undergone three major transformations, and we are in the beginning of the fourth. Each transformation has brought great benefits to the industry, mainly in terms of efficiency and productivity, in such a way that the manufacturing processes that were carried out manually before the start of the third industrial revolution are expected to be fully automatized in the fourth. The Industry 4.0 was introduced in the Hanover Trade Fair in 2011 as a concept to denote the new generation of connected, robotic, and intelligent factories. Between their characteristics, we have that it promotes new ways of production on which the manufacturing process actors interact in order to allow a self-organization of the manufacturing process, making an efficient use of human and physical resources that's allowed to reconfigure the factories in shorter cycles than the traditional one. Some requirements of Industry 4.0 are autonomy, which means that the manufacturing process actor must make decisions by themselves and perform their tasks in the most autonomous way. Technical assistance means that the new human actor must collaborate to guarantee safe working places for the human and help them to accomplish their tasks in the shortest time. Information transparency means that we need to create a digital copy of the environment by using the data collected through the sensor and other devices deployed in the manufacturing line. Interoperability means that all the manufacturing process actors must have connectivity and communication capabilities and promote most advanced processes for coordination, cooperation, and collaboration. I identify the technologies, concepts, and elements typically used to bring solutions in Industry 4.0, and we can note that those elements are vast, but we can highlight the use of artificial intelligence and internet technologies. Also, Cisco have identified the actors that interact in manufacturing processes as things, which mean any device deployed in the manufacturing line, like machines, sensors, etc. Data is raw data produced by other actors or data stored in organizational data sources. People represent a human performing tasks related to the manufacturing process, and processes represent the manufacturing process itself or other internal or external processes that are needed to accomplish the manufacturing process work. Now, I'm going to describe the problem starting from the challenges of Industry 4.0. In Industry 4.0, we need to create some standards in order to guarantee the functionality of the whole manufacturing process. We need to deal with integration and interoperability issues to guarantee, to allow the self-organization of the factory. Also, dealing with the security, privacy, and heterogeneity of data is essential due to the diverse elements deployed in production lines. Moreover, solving complexity of planning and decision-making challenges will allow the system to will allow the autonomy of the system. And finally, to allow different factories to collaborate, it's necessary to deal with the challenges of negotiation and convergence. In this Tesis project, we are interested in the challenges of integration and interoperability and complexity of planning and decision-making. We take this decision based in the state of VAR that we are going to discuss in the next slide. This state of VAR gave us many insights of the areas on which I will place my contributions. I classify the previous research work according to the integration level to which is best fit. I also identify the actor for which they allow the integration. We can notice that the coordination level was the least studied level, which means that we need to place some contribution at this level. And also, we noticed that the previous research were mostly interested in allow interoperability between of one single actor, in this case, the thing actors, in part because they use Internet of Things as integration media, which consider only thing as the actor. It means that we need to make some work at the connection and communication level in order to allow the integration of all the manufacturing process actors. Also, any previous research work allowed the integration of all the actors across all the integration levels. But to do that, we need to deal with the challenges of decision-making and complexity of planning in order to create the knowledge bases needed to allow the self-organization of the manufacturing process actors at the levels of coordination, cooperation, and collaboration. Also, to create those knowledge bases, we need to get extract information from different data sources, but previous work considered only data as source to extract knowledge. Moreover, notice that the multi-agent system was a technology typically used to bring solutions at the coordination, cooperation, and collaboration level. It means that we need to do some consideration regarding this aspect. In this sense, this thesis objective is oriented to allow the integration and interoperability of all the manufacturing process actors across all the integration levels, and to allow the self-organization of those actors at the levels of coordination, cooperation, and collaboration. We need to create knowledge, gathering information from different data sources, and we also need to consider other Industry 4.0 requirements like because we need to create scalable solutions, and for that we need to use the cloud computing paradigm. We need to allow the autonomy of the system, and we need to let those processes that have real-time necessity to work correctly. Now, I move to my first contribution. It is an autonomy and reference architecture for integration on the Industry 4.0. This architecture was called AIFE 4.0, and this is made up of 3 layers. In the physical layer, we deploy all the manufacturing process actors, but we noticed that the process actor was changed by a service actor because a process can be characterized as a service using the Internet of Service paradigm. Moreover, at the integration layer, we use Internet of Everything and as integration media because it considers not only things, but also data, people, services as the actors, and we can allow the integration and interoperability of all them. In this layer, we deploy the business process as a service using a business process as a service cloud computing model. This layer was introduced in order to deal with integration and interoperability issues. Then we have the reflective layer. In this layer, we use the autonomic computing and the everything mining in order to add autonomic capabilities to the system and guarantee the autonomy. The everything mining allows us to collect information from different data sources that is used for decision making. We can extract information from data using data mining, from things using the EKG proposed by Su et al., from services and processes using service and process mining, and from people using, for example, sentimental analysis. As AIFE allows adding autonomic capabilities incrementally, we can start allowing connectivity of the actors. Then we can allow the communication among actors. Next, we can promote other self-organization processes for coordination, and next, self-organization processes for collaboration and cooperation. This layer was added in order to deal with the complexity of planning and decision-making challenges. Now, we pass to my second contribution. In this case, we build a module for multi-agent system and cloud computing integration. To show the problems around the multi-agent system cloud computing integration, I'm going to suppose that we want to deploy the AIFE architecture into a manufacturing line. Then we have identified all the manufacturing process actors at the physical layer, and in the integration layer, we created a cyber-physical system where we characterize all the physical actors as software agents. Those agents can interoperate using multi-agent system protocols, communication protocols, and languages. And they can communicate with their physical counterpart using the sensor and effectors. Part of the reflective layer of AIFE is deployed at the cyber-physical system because here the agents can make decisions by themselves. Then we have the Internet of Everything as integration media and other elements of the manufacturing processes are deployed in the cloud. We have, for example, the knowledge bases, deployed services, business processes that are needed in the manufacturing process as services, and the business process itself is a service. The limited capability of the physical actor can be extended with services in the cloud by using, for example, to gain processing and data storage capabilities. What is the problem with this configuration? Well, here we can identify an integration problem, because although we characterize all the agents, all the physical actors as software agents, and we guarantee the interoperability of actors by using multi-agent system protocols, we have other elements in the cloud, and agents and services cannot communicate naturally. In this sense, the business process agent cannot communicate with its corresponding part, because one is an agent and the other is a service. Also, if the agent wants to use the knowledge bases to make decisions, they cannot, because of the communication limitations. Moreover, if we have a service composition in the cloud, if we want to add some agent capabilities to this composition, is not possible because agents and services cannot communicate. This is our interest in adding, in solving this problem. We need to add other elements to this configuration. And in first place, we added a web service agent, which is in charge of perform all the necessary transformation for agents and services to communicate. Moreover, we added a web service-oriented agent, which is able to deploy the agent capabilities as services in the cloud, so that any service can start invoke those capabilities directly, naturally. Moreover, as cloud computing-based system has known issues of real-time and low latency, we decided to add a third component. This configuration will allow a full integration and interoperability of the manufacturing process actor, because we can use multi-agent system protocols and cloud computing protocols for communication, and the communication module allow the integration as agents and cloud services naturally. We also have the possibility of extend the actor capability with services in the cloud, and we added a fourth component to deal with real-time issues. The autonomy of the system is managed by the multi-agent system, and we also can access some self-organization process that can be deployed at the cloud autonomously. The agent can use those services in order to self-organize the factory. Now I want to show the functionality of the agent and services communication. In this case, we have an agent that wants to invoke a service. This service can be on the cloud or in the phone. We need to remark that those services, the services in the fog, are used only when a request has real-time need or low latency need. Then we start communicating. The requesting agent sends a request to the web service agent that characterizes that service in the platform. The web service consults the fog in order to know which service which copy of the service is most involved in the cloud or in the fog, depending on the request need. Next, we get information from the system monitor. The system monitor returns the information regarding the overload of the service in the fog. See, this information indicates that the service in the fog is overloaded, then we decided to invoke a copy of the service in the cloud. Otherwise, we consult the ontology in order to know if the current request has real-time or low latency necessities. If that is the case, we invoke the service in the fog, else we invoke the service in the cloud. This information is sent to the web service agent. The web service agent translates the message to a message understandable by services. The corresponding service is called, is invoked. It returns the response, the result, and the web service agent translates this information to an agent language, and the information is forwarded to the agent. In this case, we can see that those agents can communicate, agent and services can communicate naturally because the requesting agent doesn't need to do any other transformation. It's only start a normal agent conversation. To evaluate this contribution, we made some qualitative comparison with previous work using metrics, criteria of communication and real time. And we can notice that although all the research work allow multi-agent system and cloud computing to communicate, not all allowed to do this bidirectionally and autonomously. Moreover, although some research work allowed to add the fog computing to deal with real-time needs, not only enable this component autonomously. In this case, we can notice that our proposal accomplished with all those criteria, which means that in qualitative terms, our proposal is better than the previous research. I wanted to make a comparison using metrics of the other research work, but any previous work provided those metrics. Only Mohamed et al. Show a case study that can be used for comparison. That's my interest in comparing with Mohamed et al. And for that, I reproduced the case study of Mohamed et al. Using my communication module, and I measure the time for services in the fog. It means a request that has real-time necessities, and for services in the cloud, for those requests that doesn't need real-time necessities. And we can notice that the time of my communication module in blue is always low than the time of the Mohamed et al., which means that our proposal is better in terms of performance against Mohamed et al. Then, to evaluate the real-time capabilities of the system, which are characteristic that we need to incorporate in a manufacturing process, we made some experiments. For that, I created a simulated environment using Jade as agent platform, Apache CXF as serving framework to deploy the services in the cloud or in the fog. We use different number of service requests, starting from 10 service requests by second until 100 service requests by second. The service processing time was set to a fixed value because we just want to measure the processing time of the communication module. We test the communication module without the neighbor and without the saver in order to make comparison. And the processing time for requests in the fog and in the cloud were measured separately. In the first experiment, we assume that 20% of the requests are going to need real-time processing. And we can notice that when fog is disabled, in blue, the request in the cloud, the processing time for requests in the cloud is higher than when the processing time for requests in the cloud when fog is enabled. Also, we can notice that the processing time for service in the fog, it means those requests that need real time, is always low, almost zero. We made another experiment assuming that 80% almost all the requests are going to need real-time processing, and we got similar results, which we can see basically the same graph. We noticed that the service in the fog, the processing time for service in the fog is low, almost unactive. Based on this result, we can say that this system is able to work in manufacturing processes that has real-time needs. Now, I'm going to check the achievement after this second contribution. Until now, so far we have we have created a reference architecture for Industry 4.0 that allows integration and interoperability of factors and promote processes for coordination, collaboration, and cooperation. But also we place a contribution on the communication module in order to guarantee that all the components of a manufacturing process can communicate, including services, agents, whatever. Then, we also show that the case study, the sample that we presented at the beginning of this second contribution, we use part of the reflective layer is deployed in the cloud, which means that this is cloud-oriented. Also, the multi-agent system manages the autonomy of the system, and we demonstrate with the case study that this system can work in processes that need real-time capabilities. We still need to work at the coordination, cooperation, and collaboration, and we need to show how to gather information from different data sources. For that, I move on to my third contribution, on which I created a self-coordination I designed a self-coordination process, and I implemented a self-supervisory system. This self-coordination process was characterized as an autonomy manager using autonomic computing, which comprises 3 autonomy cycles. The first cycles apply different everything mining technique in order to collect information from different data sources that allow to design the coordination plan. This plan considers variables like the availability of factors, tasks, role, processing time, etc. Also, the self-supervisory system, self-supervision autonomy cycle, is able to build different data models for failure prediction and detection, so that we can determine if the coordination plan is executing correctly. If we detect or predict any failure, then we need to repair the system calling the self-reconfiguration autonomy cycle, which also applies different data analytical mining technique in order to redesign the coordination plan according to the current context. We decided to implement the self-supervisory system because some authors say that the implementation of a self-supervisory system using artificial intelligence and techniques is a missing word. Also, we consider that putting in execution the coordination plan without the corresponding supervision will lead the manufacturing process to undesired behavior. Now we pass to show the design of this supervisory system. And here we can see the components. We have the business process from which we can extract the data. And we also have 3 data analytical tasks. The first data analytical task uses the business process data to build a model that represents this manufacturing process. And we can use this model to detect failures. The second task is a predictive model. It's able to build a predictive model using a control variable of the process data. The diagnostic model uses the previous task 1 and task 2 in order to get a diagnostic of the system, so that if a failure is detected or predicted, we invoke the self-repairing autonomic cycle. Now, I'm going to show the functionality of the supervisory cycle. Before the start of the manufacturing process, task 1 and task 2 are invoked in order to build the knowledge model, in this case, the process model and the predictive model. Then, those models subscribe to the message queue to get informed about all the events that happen in the business process, and the process graph is sent to the diagnostic model so that it can show it to the operator. The business process publishes the data during the manufacturing process, and the message queue forwards this data to the diagnostic model as event, to the prediction model as context variables, and to the process model as events. This data is processed by the predicting model and the process model, and the result is sent to the diagnostic model. The diagnostic model made a decision in order to detect failures or predict failures, and in that case, it reports the failure to the operator and invokes the self-repairing autonomic cycle. To evaluate this contribution, we use a data set of the bus industry published in Kaggle in 2019. Why we decided to use the bus dataset? Well, first, because we need to test our contribution, our supervisory system in a real environment. And we were not able to collect that data in any industry. Moreover, not many industries are open to publish their data on internet. And if they do that, they remove all the usable information. This bus data set comprises 2 years of production data, more than 4,000 context variables. It's completely anonymized but usable. It's highly imbalanced, which in this case we have only 7,000 parts for the quality control test of over 1 million. It has a variable that can be used to build one of the components of the self-supervisory system, in this case, the predictive model. And also, it contains the information that we need to build the process model and to reproduce the manufacturing process as in real, so that we can diagnose, we can get a diagnosis of the system as we were working in the reality. Now, we pass to the implementation of the first component, the process model. And for that, we use a process mining technique. In this case, we need to transform the bus data set in an event log, because the process mining is based in event logs. We use the manufacturer part as the case ID, the station as the activity, and the time when the part each process in each station is set to the timestamp. The resource was not necessary in this research, so then we apply a Python algorithm that converts the dataset into an event log that contains more than 15 million events. This event log is sent to the process mining tool, and it returns the process graph that contains all the information about the system. This graph is transformed into a file that can be used in the diagnostic model to make decisions. In this case, we have the actors, we have the overall processing time, the transition between actors, the processing time on each station, and also we can have bottlenecks, etc. This information can be used to make decisions regarding the performance of a station and the overall manufacturing process. Then we pass to build the second model, the predictive model. In this case, we use the data set directly, which contains all the context data. 500,000 samples were used over more than 1 million, and 400,000 were used for training and 100,000 for testing. We trained 3 different classifiers, in this case, the balanced random forest, the balanced bagging, and the linear discriminant analysis. From the confusion matrices, we can get many information that allow us to select the algorithm that best fit the data. However, we measure that the metrics not typically used in this type of tasks to select the best classifier. We can see that LDA, the one score for LDA is almost 100%, which means that this classifier is very good at detecting which parts pass the quality control test, but for the fair class, it's only 80%, which means that it's not good at all. This happens because the data is very imbalanced. Then we look at the matching correlation coefficient, and we notice that it is almost 0, which means that a random number can give us better results than this classifier. Then we move to the balanced bagging and balanced random forest classifiers, and we look at the matching correlation coefficient, and it is almost 1, which means that both algorithms are good at predicting both classes. Finally, select the classifier that is going to act as predictive model. We plot the receiver operating curve of both algorithms, and we can notice that the balanced bagging has a curve with less disturbances, and also its area under the curve is 1, which means that this algorithm, we must use this algorithm predictive model. Then we pass to build the diagnostic model. In this case, we created an application that uses the training data as data source, from which we extract the manufacturing process event. It will reproduce then in the diagnostic model. We can see here the stations, the manufacturing process graph, the station, and the parts that are in production. Also, this diagnostic model uses the predictive model to detect failures. In this case, it predicts that some parts are going to fail the quality control test at different hours of the day. And for that, we need to relaunch the cell reconfiguration cycle. Also, we detect that the performance, we detect failures at the station level regarding the performance of of those stations, the historical performance, the diagnostic model was able to group the failures if they occur at the same time, so that we don't need to reconfigure the autonomic process. We need to reconfigure the autonomic process only one time. To evaluate this classifier, we made a qualitative comparison to related work, and we noticed that our approach is the only that applies several everything mining techniques to collect information from different actors, in this case, the data actor and the process actor. Then our supervisory system is able to process big volumes of data and also is able to act in real time. It is the only approach that uses a process mining technique to get information from the process that allow us to make decisions and detect failures. We can collect information from different actors. Also, the diagnostic model support the inclusion of new everything mining models for decision making, and the autonomy of the supervisory system is high because the diagnostic model doesn't need to make decisions by itself. To evaluate the real-time capabilities of the system, we measure the time for failure detection and the time for quality control test prediction of the diagnostic model, and we notice that it is very low, what could indicate that this supervisory system can act in system with real-time necessities. Now, we are going to make a checkpoint on the second contribution, starting from the goals that accomplish the first and the second contribution. In this case, we designed a self-coordination autonomic manager that can be used for self-organize the factory, and we also demonstrate how to gather information from different data sources. Okay, conclusions. In this Tesis project, I was able to build a reference architecture for integration of actors in manufacturing processes that allow us to deal with the integration and interoperability challenges, and also with the decision-making and complexity of planning by promoting self-autonomic processes for coordination, cooperation, and collaboration. Moreover, we built a communication model that ensures the integration of all the actors, including services and agents, and we demonstrate that this proposal can work in real time. Also, we designed a self-autonomic manager for self-coordination, and we implemented an self-supervisory system using real data of an industry. Well, the perspective. In future, it will be, it must be interesting to test our contributions in a real factory, because although we use real data, the self-supervisory system is not working in a real environment. We also need to implement the self-configuring and self-reconfiguring autonomy cycle of the coordination process in order to allow the manufacturing process to be fully coordinated. We need to implement and design the autonomy manager for self-cooperation and self-collaboration to allow a full integration of the manufacturing process. Improving the self-supervising application will be other interesting perspective, because we can add, in this case, the algorithm for process mining directly in the to the diagnostic application, so that we don't need to depend on external tools. We can incorporate new everything mining technique to the framework. For example, I think mining, like proposed by Suetar, to get a full diagnosis of the machinery deployed in the production line, people mining to get information from people using, for example, sentimental analysis. And we can incorporate new communication languages to the multi-agent system, cloud computing component, so that they can communicate with services that use different communication languages. During the development of this Tesis project, we created 5 papers, and we published 4 in different prestigious journals, and we still have 1 waiting for acceptation. Okay, I cannot finish the presentation without saying thank you to the PhD committee for evaluating my proposal, and especially to my supervisors for giving me the opportunity of develop such interesting topic. Thank you.
Yeah, ok. Donc Manuel, vous avez présenté de façon claire et pédagogique vos travaux de recherche consacrés à la question du processus autonomique pour l'industrie 4.0, plus particulièrement les problématiques liées à l'intégration et l'interopérabilité. Le jury a souligné que votre exposé a mis en lumière un travail original et innovant présentant une industrie 4.0 sur une architecture 5C, qui est votre proposition. 5C pour connexion, communication, coordination, coopération et collaboration. Votre travail s'appuie sur un large spectre de compétences allant de l'autonomic computing, des systèmes intelligents, en passant par des techniques du cloud, jusqu'au X-mining. Vous avez fait un gros effort de positionnement de votre thèse par un état de l'art conséquent, mais néanmoins, nous avons apprécié en tant que jury votre façon d'aborder les choses synthétiquement, facilitant la compréhension des problèmes abordés par rapport à chaque objectif fixé. Vous avez démontré la maîtrise de votre sujet, autant d'un point de vue théorique, par la conception de cette architecture 5C, ainsi qu'appliquée par les nombreuses évaluations et expérimentations que vous avez faites. Vous avez répondu aux nombreuses questions du jury, confirmant aussi votre grande maîtrise de ce sujet. Pour toutes ces raisons, le jury vous décerne à l'unanimité le grade de docteur en informatique de l'Université de Pau et des Pays de l'Adour. Congratulations.
Merci beaucoup. Merci beaucoup. Bon. C'est très, très heureux. Je me sens très heureux dans ce moment pour cette bout que j'ai, je ne sais pas comment dire en français, mais...
Español, lo puedes decir en español. Si
no, bueno, me siento de verdad muy contento por este logro que he obtenido, por el crecimiento a través de estos años, en compañía del profesor, de mis 2 supervisores que me han ayudado a lograr esto, por medio del cual pues no solamente he aprendido diferentes lenguas, francés, inglés, sino también obtuve un conocimiento en un área pues, que yo no dominaba. Y pues de verdad me siento muy contento y les agradezco a ustedes, mis 3 miembros del jurado, la profesora Audín, la profesora Lemois y el profesor José Gutiérrez, por haber evaluado la propuesta también. Muchas gracias a todos.
Félicitations à vous, c'est un gros travail que vous avez fait. Vous avez fortement apprécié.
Merci, merci.
Bon, mais merci beaucoup. Merci beaucoup à tous.
Oui.
Bonne continuación.
Felicitaciones también.
Merci.
¿Cómo se dice? ¿Una buena continuación? ¿Sí?
Sí.
Se puede.
¿Me puede decir? ¿Cómo se
Sí.
dice?
Sí.
Buena,
Está bien.
buena suerte.
Éxito,
Sí.
suerte, éxito en el futuro,
Suerte.
éxito en tus proyectos futuros. Bueno, el pot de test, il nous le doit.
Ah,
Il va falloir le prévoir.
Vous êtes invité à visiter mon université, un site du patrimonio mundial et par conséquent, votre patrimonio. Ok. Os espero aquí.
Gracias.
Gracias.
Seguro.
Bueno,
Bueno, pues muchas gracias a todos. Merci beaucoup.
Ernesto, te mando la atestación, ¿oíste?
Parfait. Très bien.
Ya la deberías de tener también en tu correo. Y si no, me avisas, pero ya la mandé.
Seguro. Seguro.
¿Y cómo se dice? Felicitaciones, doctor. Doctor.
Felicidades, doctor.
bien.
Felicidades, doctor.
Merci. Gracias, muchas gracias.
Venga, nos vemos.
Ok.
Bueno,
Bueno, vale. Muchas gracias.
Excelente.
Gracias a todos.
Bueno.
Merci beaucoup. Au
Ah,
revoir.
Gracias a todos.
Nos vemos.
gracias.
Hasta
Una visita
luego.
al Alcalá, ¿eh? Una visita al Alcalá de Henares. Hace falta.
Sí, ¿verdad? En lo que se pueda, en lo que abran las fronteras.
Sí, sí.
Adiós, adiós.
Adiós.
Adiós, gracias.
Gracias por el
Adiós.
tiempo.
Merci à tous. Hein. Merci beaucoup. Ciao.
Merci pour l'invitation.
Avec plaisir. La prochaine, c'est en vrai.